Hi friends, welcome to somethingcalledscience.com. Today we'll talk about the fascinating topic of oxidation numbers in transition metals. You can find the full transcript and a worksheet on our website. Have you ever noticed how iron can rust into that familiar reddish-brown color, or how copper statues turn green over time? These color changes hint at something fascinating happening at the atomic level, namely transition metals changing their oxidation numbers. While this might sound complicated, understanding oxidation numbers is actually quite accessible once you grasp a few key concepts. Before diving into transition metals specifically, let's understand what an oxidation number actually means. Think of an oxidation number as a bookkeeping system for electrons. It tells us how many electrons an atom has gained, lost, or is sharing in a chemical compound. When an atom loses electrons, it becomes positively charged, and its oxidation number or oxidation state is positive. When an atom gains electrons, it becomes negatively charged, and its oxidation number or oxidation state is negative. For most everyday elements, this is pretty straightforward. Sodium always wants to lose one electron, so it typically has an oxidation number of +1. Chlorine loves to gain one electron, giving it an oxidation number of -1. When they combine to form table salt, sodium chloride, sodium gives up an electron to chlorine and everybody's happy. Now here's where transition metals get interesting and break the pattern. Look at the middle section of the periodic table, the block of elements including iron, copper and manganese. These are transition metals, and unlike sodium or chlorine, they don't stick to just one oxidation number. They're flexible, capable of losing different numbers of electrons depending on the situation. Iron is a perfect example. Sometimes iron has an oxidation number of +2, which we call iron 2 or ferrous iron. Other times it has an oxidation number of +3, called iron 3 or ferric iron. Both forms are stable and commonly found in nature and in the lab. And this flexibility is what makes transition metals so versatile and useful in chemistry and industry. So as we just saw, the Roman numeral in parentheses tells you the oxidation number of the transition metal in that specific compound. So when you see iron 2 chloride, the iron has an oxidation number of +2. Iron 3 chloride, the iron has an oxidation number of +3. In copper 1 oxide, the copper has an oxidation number of +1. And in copper 2 sulfate, the copper has an oxidation number of +2. This naming system exists precisely because transition metals can have multiple oxidation states. We need a way to specify which version we're talking about, since iron 2 chloride and iron 3 chloride are completely different compounds with different properties. You might also encounter an older naming system that uses Latin-based names with different endings. The OUS ending stands for lower oxidation states, and the IC ending stands for higher oxidation states. For example, ferrous is iron 2, ferric is iron 3, cuprous is copper 1, and cupric is copper 2. The Roman numeral system, also called the stock system, is more modern and preferred because it's clearer and works for metals with more than 2 oxidation states. With the old system, you'd run out of endings pretty quickly. So why can transition metals have varying oxidation numbers? The answer lies in their electron configuration, or how electrons are arranged around the atom. Transition metals have electrons in what chemists call d orbitals. Without getting too deep into quantum mechanics, think of these d orbitals as special parking spaces for electrons that are close enough in energy to the outermost electrons that they can also participate in chemical reactions. Regular elements typically only lose or gain electrons from their outermost shell. Transition metals, however, can lose electrons from both their outermost shell and from these d orbitals. This gives them multiple options for how many electrons to give up, resulting in multiple possible oxidation numbers. Imagine having a wallet with bills in both the main compartment and a hidden pocket. Regular elements can only spend money from the main compartment, but transition metals can access both, giving them more flexibility in their transactions with other elements. While transition metals can theoretically have many oxidation numbers, certain values are more common and stable than others. For instance, copper commonly appears as +1, which is copper 1, or +2, which is copper 2. The green patina on old copper structures is actually copper 2 carbonate, while copper 1 oxide gives a reddish color. Copper 1 oxide, Cu2O, is reddish because of how its electrons are arranged when copper is in the +1 oxidation state. This compound absorbs certain wavelengths of light and reflects the red wavelengths back to our eyes. On the other hand, copper 2 carbonate, CuCO3, or basic copper carbonate, which forms the green patina, has copper in the +2 oxidation state. This compound has a different electron arrangement, so it absorbs and reflects different wavelengths of light, giving it that distinctive blue-green color. So the why comes down to quantum mechanics and how electrons interact with light, which gets quite complex. But the simple version is, when copper loses one electron, becoming +1, versus 2 electrons, becoming +2, the remaining electrons are arranged differently. This changes which wavelengths of visible light the compound can absorb, which directly determines what color we see. This color change based on oxidation state is actually really common with transition metals. The transition metal manganese is particularly versatile, with stable oxidation states ranging from +2 all the way up to +7. The deep purple color of potassium permanganate, a common disinfectant, comes from manganese in the +7 oxidation state. As another example, chromium commonly exists as +3 or +6. Chromium 3 gives rubies their red color, while chromium 6 compounds are bright yellow or orange. For example, chrome yellow paint pigment was historically used in school buses, road markings, and art paints. So why does this matter? Well, understanding oxidation numbers in transition metals isn't just academic, it has real-world importance. The different oxidation states of transition metals often have dramatically different properties, including different colors, different levels of toxicity, and different chemical behaviors. Right now, iron atoms in your blood are changing their oxidation state with every breath you take. When iron switches from +2 to +3 and back again, it can grab oxygen in your lungs and release it to your muscles and organs. Without this ability to change oxidation states, you couldn't breathe. In factories and cars, transition metals are used in cars to clean up exhaust fumes. The catalytic converter in your car uses 3 transition metals, namely platinum, palladium, and rhodium, to turn poisonous exhaust fumes into safer gases before they come out of the tailpipe. In environmental science, understanding chromium oxidation states is critical for keeping our environment safe. Chromium 3 won't hurt you. In fact, your body needs a little bit of it. But chromium 6 can cause cancer. If a factory spills chromium 6 and it gets into the ground or water supply, cleanup crews need to change it into the harmless chromium 3 form to make the area safe again. So how do we determine oxidation numbers? When you encounter a compound containing a transition metal, you can figure out its oxidation number using a few simple rules. Using these rules, you can figure out a transition metal's oxidation number like solving a simple math puzzle. We will explain these rules in more detail in another video, but for now, here are the basic rules. 1. In any compound, all the oxidation numbers must add up to 0, like balancing a checkbook. Rule 2. Oxygen is almost always -2. And Rule 3. Hydrogen is almost always +1. Here are some helpful steps for how we can figure out the oxidation state of transition metals, and really any element, in compounds. 1. Determine the oxidation numbers of elements that are well known based on the rules that we discussed. 2. Create an equation where the sum of the oxidation numbers equals the overall charge of the compound or ion. And 3. Use algebra to solve for the unknown oxidation number. Let's try an example with copper oxide, CuO. This compound has one copper atom and one oxygen atom, and we need to figure out the oxidation number of copper. Step 1 is to identify known oxidation numbers. Let's call copper's oxidation number X, and we know that oxygen almost always has an oxidation number of -2. Step 2 is to set up an equation where the sum of the oxidation numbers equals the overall charge of the compound or ion. Our compound CuO is neutral, meaning that it has no electric charge, so copper and oxygen must add up to 0. X plus -2 is 0. In step 3, we now solve for X. X minus 2 is 0, so X is +2. Hence, copper has an oxidation number of +2, so this is copper 2 oxide. Let's try one more example, the chromate ion, CrO4 2-. In this example, we need to figure out the oxidation number of chromium because we already know that oxygen has an oxidation number of -2. In step 1, we let chromium's oxidation number be X. We have 4 oxygen atoms with each a known oxidation number of -2, so 4 times -2 is -8. In step 2, we set up the equation. The charge of the ion here is -2, so we need to add up to -2. X plus -8 is -2. In step 3, we solve for X. X minus 8 is -2. X is +6. Hence, chromium in the chromate ion has an oxidation number of +6. Summing up, transition metals' ability to exist in multiple oxidation states makes them the Swiss Army knives of chemistry. They're versatile, adaptable, and incredibly useful. And this is because they're flexible and capable of losing different numbers of electrons depending on the situation. A big thank you to our Patreon members. You're all awesome and helping out the channel a lot. You can find the full transcript of this video and a worksheet on our website. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more science content. It really helps the channel out. Let us know in the comments if you have any questions or topics you'd like us to cover next. Thanks for watching and see you in the next video.